NASA released fresh images showing interstellar comet 3I Atlas, glowing in a shade of green, a dramatic shift from its earlier red hue. The change has sent ripples through the astronomical community, amplifying existing mysteries about this rogue visitor and stirring fears over what secrets might lurk within. The color evolution is not just cosmetic. It may hint at processes in action that defy standard comet models. As the object plunges deeper toward the Sun, astronomers are scrambling to interpret what is happening, and many are unsettled by the implications. From the moment 3I Atlas was discovered on July 1, 2025, it drew wide attention. It was already the third confirmed interstellar object ever observed, following Oumuamua in 2017 and Comet Borisov in 2019. Its trajectory, velocity and orbit clearly mark it as an interstellar wanderer. It is on a hyperbolic path through the solar system, destined to depart eventually rather than to become bound. In the months since discovery, its evolving cloud of dust and gas, its coma, had displayed typical behaviors: gradual brightening, the development of a faint tail, and the release of gases under solar heating. But the sudden color shift is something far less ordinary. Earlier observations, including photometry through NASA's Atlas network, documented how the comet's CO color index, comparing light in bluish to orange-red bands, steadily moved from a more reddish value toward a more neutral or solar color. That gradual shift had been understood as dust from a reddened surface, giving way to increased release of icy grains and a changing optical depth in the coma. But then as 3I Atlas continued its inward journey, imaging and spectroscopic data began indicating a more abrupt transition. Its coma's glow reddened earlier, but now appears green. The contrast is stark and puzzling. One moment it is tinged red, the next moment glowing green, and that leaves astronomers confronting more than an enigma of pigment. It raises questions about what physical and chemical machinery is operating inside. Why green? In comets bound to our solar system, dramatic green hues have occasionally been seen and are often traced to molecular species such as diatomic carbon, C2, which fluoresces under solar ultraviolet radiation and gives off green light. But in 3I Atlas, spectroscopic data thus far have not confirmed strong emissions of the usual suspects in green comets. Instead, the emerging fluxes of cyanide, CN radicals, and nickel atoms have been flagged in the comet's outgassing. The appearance of nickel is itself unusual. Many comets show metals only weakly, if at all, and nickel lines are not commonly strong enough to dominate a comet's color signature. What's more, the pattern in which these species appear is not linear. Some analyses suggest their emission rises superlinearly, faster than simple temperature scaling, as the comet nears the Sun, hinting at a threshold or switch-like activation process inside the body. That kind of nonlinearity unsettles those who expect the behavior of a comet's surface and interior to remain fairly monotonic under increasing solar heating. The transition from red to green likely coincided with the appearance of a visible anti-solar tail in 3I Atlas and a break in the slope of its brightness curve. Before that moment, the comet's brightness increased rapidly with decreasing distance, consistent with dust liftoff from a reddened surface. Afterward, the growth slowed, consistent with a shift in the dominant source of scattering particles. For example, small ice grains instead of larger red dust, and changing optical depth in the coma. Some models propose that early in its inward journey, the dust grains lifted carried a red tinge, perhaps from processed organics or tholins typical of distant outer solar system bodies. Later, as volatile ices closer to the surface began sublimating more vigorously, the coma population honored more transparent bluish ice grains, pushing the integrated color toward green. But for many astronomers, that adjustment of dust and ice populations feels insufficient to explain not just a steady drift in hue, but a relatively abrupt jump. The fear is, what if deeper processes, unexpected chemistry or internal structural features are now revealing themselves, threats to existing cometry theories? If 3I Atlas hosts volatile reservoirs or trapped compounds unlike those of Oort cloud comets, we might be witnessing a new class of behavior. Perhaps it carries exotic ices or compounds that don't sublimate at typical rates, or compounds that remain dormant until a specific thermal threshold is met, The green glow may be a signal that those compounds are now being unleashed, perhaps in bursts or scattered pockets. That alone would upend assumptions about how interstellar bodies evolve under solar influence. More unsettling is the possibility that the object's internal structure allows for sudden propagation of heat or gas pressure, causing a cascade of activity that shifts the dominating light-scattering regime. If the comet's outer shell is insulating, heat might build in subsurface layers until it propagates through cracks or vents, opening fresh regions and activating new volatile zones. That could mean color changes that are spatially heterogeneous and temporally abrupt. Observers fear that they may have passed the point of gradual approximation and are now seeing discontinuities, jumps in activity rather than smooth transitions. The recorded presence of nickel in the coma is itself a red flag. Metals among comet vapors are rare and often minor trace signatures. In 3I Atlas, nickel may suggest decomposition of metal-bearing compounds or sublimation of metal complexes more akin to planetary materials than standard comets. If those metals come from within the nucleus, rather than surface contamination, that indicates a surprising internal composition. Nickel combined with cyanide emissions may hint at exotic organometallic chemistry, or perhaps remnants of mineral phases not commonly volatile in typical solar system comets. Some astronomers worry that the dramatic color shift could be a signal that 3I Atlas is not a simple inert icy body, but might host internal energy gradients, fossil radioactive heating, or hidden reservoirs of unusual volatiles. If so, the implications extend beyond one comet. It challenges how we imagine interstellar bodies are constructed, processed, and preserved over eons. There is also the possibility of evolving optical depth in the coma. If outgassing becomes strong, the coma might become dense enough that its own scattering and absorption behavior changes, masking or amplifying particular wavelengths differently. In that case, the sudden shift from red to green might be less about compositional changes and more about radiative transfer effects in a dynamic cloud of particles, but such a scenario requires finely tuned conditions. It would demand a steep rise in particle density, sudden particle size changes, or optical thickness thresholds. That precise tipping point behavior makes theorists anxious because in real cometary comas, the transitions are often more gradual and predictable. Another angle of concern comes from the fact that 3I Atlas's color shift corresponded with a break in its light curve slope. Before that moment, its brightness rose steeply as it approached the sun. Afterward, the rate of brightening slowed. That suggests something fundamental changed in how its coma evolves, whether in dust production rate, particle size distribution, or gas-dust balance. Some models propose that the comet shifted from a dust-dominated scattering regime to one dominated by more transparent icy grains. But some astronomers fear that the cause could be deeper. Perhaps deeper volatiles from interior layers started to dominate, gradually eclipsing surface modes of emission. In that view, the color change is a visible symptom of a wholesale shift in how mass is lost from the body, and that hints at structure and composition unexpected in comets known to us. What further heightens concern is that 3I Atlas does not neatly mirror our best-known interstellar predecessor, 2I Borisov. In Borisov, behavior was broadly consistent with a cometary template, predictable tail evolution, and spectral signatures of known molecules. The greenish comae of some solar system comets have likewise been tied to familiar molecules like C2 and CN. But in 3I Atlas, the event feels more radical, a color change happening in the middle of its solar encounter. It's not merely appearing green near perihelion, but shifting color along the approach. That dynamic behavior is not well captured by existing comet models of thermodynamics, sublimation, or dust dynamics. Astronomers fear this may be a sign that interstellar comets harbor structural or chemical diversity far beyond our solar system analogues. One compelling but unsettling idea is that 3I Atlas carried a primordial or lightly processed crust that prevented early exposure of interior ices and compounds. As it grew warmer, this crust might have cracked or peeled away, rapidly exposing volatile rich layers that respond differently to solar heating. That sudden exposure could initiate cascading changes in gas release, particle production and optical behavior. If that is correct, then we are witnessing in real time the unveiling of a hidden interior. But if that interior houses ices or compounds that are rare or new to science, the interpretive challenge is immense. Astronomers are also uneasy about spatial heterogeneity. The comet's color transition might not be uniform. If patchy areas of the nucleus or coma dominate over time, we might see localized green patches or shifting patterns of green and red hues as the object spins or as vents open and close.